Well, thank you very much for letting me here for this presentation. So I will talk about a topic which is a little bit outside mainstream quantum technology or quantum modeling, because actually this is a chance I came up with these agents which are actually thought experiments with robots, and then try to apply some quantum control on these agents. And so it could be somewhere between artificial intelligence, also logic. So it's a little bit an overview of this an approach. And this work was done principally by two students. Now, unhappily, they're not here because they're actually going back to one in Brazil and the other Singapore. So it was not easy to. I would be happy that we'd be here, but it was not possible. So, okay, I'll start. And well, I start with one nation word perhaps you didn't hear very often is the quantum robots, but this is actually a quite old idea in the field of quantum computing, quantum information, and it's due to Benioff, which was actually the first person to propose the idea of a Turing machine using quantum physics. So this is a famous paper, 1980, and most of the interest in quantum computing is quantum algorithms, because the idea is to overcome classical computing. But Benioff had another idea, and he said, why not think about the principle of a quantum robot, which is a first step towards a quantum mechanical description system that are aware of the environment and make decisions. So meaning that now we open a little bit the system, meaning that we can also have some virus environment, and so the system will try to adapt to this environment. So this was also a paper in 1988. And I came up with this. I don't really know these people. There's a quantum robotics group, which was founded in 2016-17, and they wrote a book. And so I just quote their introduction. They say quantum robots is an emerging engineering and scientific research discipline that explores the application of quantum mechanics, quantum computing, quantum algorithms, and related fields to robotics. These developments are expected to impact technological capability for robots to sense, plan, learn, and act in dynamic environment. So it's something new, and okay, there's not many development until now, but perhaps it's promising. Now, the other idea was that there exists concept which name is after the Valentino Braintenberg, who was a cybernetist and a professor in Tübingen of cybernetics, and he had some quite original ideas to build some thought experiments using vehicles. So there's a book which names vehicles, and here, so you can look at it afterwards. And it's a very simple device where you have sensors. So what we see is 2 or 3 sensors in front of the vehicle, and then this sensor gave signals, and then you combine the signals, and then you control the wheels. So there's some movement associated with all these combinations. And so sensors can be connected in different configurations. So basically, here you have example of 2 vehicles, 2A to B. 2A is fear, 2B is love, and meaning that depending on how you connect the wheels, well, you have the vehicle can go to the source, or you can go away from the source. Okay, so this is the basic idea. Then there's many other combinations, but what we will do is, then he said the last thing, well, this sort of philosophical conception, he calls this the law of uphill analysis and downhill invention. He says it's far easier to create machines that exhibit complex behavior, meaning just putting wires in some disposition, than to try to derive their structures from behavioral observations and interpretations, meaning that this upside down approach. Now, how do we get in this? Well, we tried now to put this quantum-like behavior, and was already some work done by several teams of principally Perkovsky, who is a logician. He has much interest also in quantum computing and robots. And so he thought of applying these Braintenberg vehicles and to put some control, and control would be basically quantum gates and some very, very small quantum computing in order to give these this behavioral analysis, but also fuzzy logic, meaning that now we will have inputs which could be some fuzzy inputs, and outputs also could be fuzzy outputs. So there's several papers on that. And so inspired by that, we proposed 2 years ago, this was in QI 2016, an approach which is called eigenlogic, meaning that in some way we can do propositional logic based on the eigenvalues of quantum observables, but not only quantum, could be projectors, could be whatever. And well, it works quite well for different fields, also to doing some quantum gates, quantum computing. So we try to see that can we apply now this method here. The goal is that the multiple combination of the logical gates using the control of the Braintenberg vehicles. So we developed visual simulations. So we realized that we show you perhaps one vehicle, but it's more a simulation, and see how these vehicles behave. So the idea is this. This will be a vehicle, and this is a light source, and then we will look what's going on when this light source is lit or not. So more or less toy experiments. Okay. Now, so some introduction about the eigenlogic method. So this is a quite simple method. What we start with qubits, meaning that we have 2 projectors which are qubit 1, qubit 0, and then actually we can build a logical function just by changing the 2 values f0 and f1 in front of the projector, and these are actually eigenvalues. Because more or less, if you look at the structure, the eigenvalues, well, in some way, they could be understood as truth values of a proposition or of a logical system. Now, you can scale up. We can go to 2 qubits. In 2 qubits, you just develop this kind of expression, and depending on the values of the various f functions, here you can have 16 possibilities. You get all the logical connectives. And for example, we can have A, B, which are the inputs, or we can have the conjunction, and we can have the XOR, and we can have implication. So it's more or less you can do propositional logic with operators. This is the basic idea of eigenlogic. Just to see this is an example. So here, for example, we have, if you look at the operators in blue, these are all the projector operators corresponding to the truth table of all the possible logical functions for 2 inputs, which is a 2-array system. But one can go up to whatever many inputs one wants, and we have unique expression for each expression. And what is interesting, this is actually the semantics of your logical system, because the truth table gives you the semantics. So you work with the semantics directly, and you got an operator for that. One thing which is new, but we'll not use it here, is that we can actually define logic not only using 0, 1, but we can also use logic in +1, -1. So it's no matter that you use 0 or 1, you can use whatever number, and in that way you can also get some other expression of the operators. More or less Pauli operators and whatever. So I have some papers on that, much more general than this. So, but I think it's quite promising, because in some ways one can rewrite many also circuits in this way. Okay. So last thing about this is that fuzzy. We can now do fuzzy eigenlogic. Now this is something which is natural in quantum physics. You change bases. You can change bases. And if you look at the block sphere, this would be for 1 qubit. Well, I can use a Born rule, which is more or less the average value of an operator, on one of these projectors. For example, if I take the projector for the 1 qubit and I do the average on some quantum state in the block sphere, well, what I get is a probability. Okay? I can trace out this. And this can be interpreted as a fuzzy membership function, meaning that it can be a part of a set, fuzzy set. And we can do the complement, and this verifies, let's say, the first condition for fuzzy logic. The other ones are also verified. So we can build now composite system, 2 inputs, 2 fuzzy inputs. And we can then define A, B as the inputs, but we can also measure conjunction and disjunction. So we can have a measure of disjunction for states which are not eigenstates, meaning whatever angle you have, I can have a measure, and in some way here, this term would be the interference term. Very special case, but it is, meaning you're not in the eigenstates. Now, okay, this is the basics. Now, what do we do in our vehicles? So the vehicles, we will define it as this kind of system. We have 2 inputs. These are the 2 sensors. So these inputs can be fuzzy, meaning it can be some value between 0 and 1, some continuous value. And then we have these operators, F and Fr, and then we have the outputs, which are signals for the command of the wheels, which will be actually the membership function. So more or less it's very simple. And what we have as input is this state, and as output we will do 2 Born rules on left and right here. So basically it's very simple. Now, what is the motion of a vehicle? We can define emotion as an emergent behavior that arises from sensor drives, effectors, and logic. And it may look human or animal, but it can also have some completely new behaviors, because it really depends on how you do connect wires and which operators you use. And so in some way, we have this image, so different conditions, sensors, vision, fusion, patterns, drives and effectors, main input, output, mapping, perception, internal state behavior, precise motion generation. This gives you an evolved emotional behavior of the robot. Now, here I will just show you, these are the emotions described by Braintenberg, which are the 4 basic emotions for a 2-wheel, 2-sensor vehicle. So we have fear. Fear is just connecting the 2 wires directly to the wheels with a plus sign. This meaning it's a positive signal. And then this is fear, so we'll see that after simulation that the vehicle goes away from the light. Then you have aggressive, you invert the 2 wires with the same sign. Then you have love, you take the minus sign, the complement. And then you have explore, you take the reverse and you complement. So these are the 4 basic emotions given by the Braintenberg vehicles. And these are some emotions we developed using, well, it was experimental, so we didn't know exactly what we did for what kind of logical function, but it turns out that these logical functions work well. It's non-implication. So non-implication of B over A, non-implication of A over B, and this gives us some passion, meaning that now the vehicle goes to the source and it becomes very wild when it's near the source, and boredom, meaning that the vehicle doesn't care a lot about the source if we invert these 2. So we didn't analyze what this means. It could be then, of course, interesting. And other 2 emotions, it's more quantum-like. We took one of the operators, which is the Hadamard gate, which is well known in quantum computing. It's double Hadamard gate, and the other one is just B. And this gives us worship, meaning the vehicle turns very quickly around the source without stopping. And then doubt, which is given by this operator, 1 minus z tensor z, the ones we saw in the last lecture before, same operator. And here we have some doubt, meaning that the vehicle is somewhere that hesitates going from one to the other. So the best thing to do is to show video. I think this would be nice. And so here we put the light sensors, and then here are the vehicles, so we can create them like that. Now here we are in fear. So you see the vehicles are afraid from the light, so they go away. Now aggressiveness, they go to the light. They really attack. Passion, they stick to the light. And worship, they are a little bit they want to show how they're proud and so on. So this is really, we didn't do any behavior analysis, we just put some wires, and this is the idea here. You have many other descriptions, and it's quite interesting to read. Okay, so small simulation now. So there's other videos, but I think we already saw them. So perhaps start with to see what's going on with doubt. Okay. So we can choose the logical function, and then we put the lights, and then so you see it's very. Oh, he's more sure of himself. Yeah, and they get also caught by that. Okay, now just to show you that the student work, they did work. It's not just amusement. This is the program, so it's Java plus and all this configuration to do some animations. Now, one thing we could see is that how could we some way classify these emotions? Well, we were inspired by there's one notion which is called the wheel of emotions. This is was given by Lucic in, well, it's quite known by behavioral analysis, and meaning that small perturbations can change emotions, and you can have some continuous image of emotion, and this is presented in a wheel. So this is one of the wheels we got, putting the different emotions, and you can go from one to the other. And the idea is these are the different logical combinations to get these emotions. So, okay, this is only the starting work. So I think we have, for this case, we have to do much more investigation. But also this notion is well known. Now, so if you resume the behavior, this is a simple behavior. The simulation of emotional states using different configurations, ideological operators, the vehicle's computation unit, fear, aggression, passion, boredom, worship, doubt. So by combining and changing logical control gates, one can tune small changes in vehicle's behavior around the basic Braintenberg emotion. What is to see technically is that the light source gives you signals, but the vehicle, when it moves, signal changes. So it's as all the times inputs changes all along the motion. So this means that if you look at it in a quantum way, it's you change the angles all the time, and so you adapt the angles. It's sort of a, I don't know if you can say it learns, but it's more or less this continuous input updating. It's automatically updated because of that. That's the interesting thing. That's why we get so much variety. Now extension would be, so this is just some thought experiments. You said, could we some way think about entanglement? Now the idea of entanglement is quite difficult, but one idea would be if the vehicles collide, it's like particles, then perhaps afterwards they're sort of entangled. So we try to do this. It's not very, let's say, rigorous from very scientific, but it can give you some image. The idea is, for example, a hydrogen molecule where one hydrogen atom is fixed spin, and when you take the molecule, this is known in physics, you get an entangled state. The ground state is what we call a singlet state. So the combination of two hydrogen atoms give you what a molecule is entangled. So the idea is here. Now, what we do is when the vehicles collide, we update one of the controls, and we introduce entanglement gates in the machine. We don't know how you would do that practically, but this is the idea. And so control naught or control z. And what we have to say is in eigenlogic, the 8 of the operators in the truth tables are entanglement gates. Okay? So meaning that and or all these are entanglement gates. Entanglement gate means that for some inputs, not all inputs, separate inputs become entangled. Not for all the angles, but there's some angles, there's some class of angles where when the signals are separated, then they become entangled inside. And it's something which is known. In quantum computing, for example, control Z, which is very simple, is an entanglement gate for the basis which is in the Higgs basis. So this is, so the idea was here. So this video is really some artistic view, but it's quite interesting to see that the complexity which comes around. Now here we have collision, and now they're entangled. The students propose this, okay, but the idea was this, that an interaction should perhaps change something in the state of the two vehicles. And then you can entangle more, 3, 4. So, okay, this is okay, so just to mention that in another project we really built one of the Braintenberg vehicles, but it was easier to use acoustic sensors, so it was based on this. And we did some fuzzy logic. Here the goal was running along a wall, so this is more or less a project which is still going on. But to say that actually it's not so difficult to build this, okay, this is I'm finished. And discussion. So currently much research is undertaken on the analysis of the interaction between a quantum computer and its environment, that should be correct codes, considered as a source of errors that must be managed correctly. On the other hand, in the present approach, the interaction between a quantum rover and its environment has to be considered as an essential part of overall dynamics of the system. This point of view is at the core of performative systems and the related strategy to manage complexity. This approach may help to measure complexity in desired applications. Also, formalization of the quantum-like Braintenberg vehicle components as quantum neural networks could lead to new investigation strategies that could benefit research in machine learning algorithms related to emotional analysis. It has been suggested that using entanglement gates in a fuzzy logic configuration makes it possible to implement quantum-associated memory learning and retrieval algorithms. These are papers which has been cited here. So, meaning that this can open some perhaps new ideas, because it's quite simple to develop this kind of vehicles. And so I just want to thank the two students which are not here. Rebeca, who is from the University of Brazil, so it's in double degree with our university, which is sometimes Paris, Paris-Saclay, and Sharma, who is from the National University of Singapore. So these are very, very brilliant students because they really got involved in this, and they really like to work on this. So I think the results are very interesting. And this is some pictures from the book. Thank you for your attention. If you have some questions,